Hello friends, here in this video we will see a problem on the unknown load and total elongation. Here we have a question. Determine the magnitude of P, which is the unknown load here, for equilibrium and total elongation of the bar as shown in figure. This diagram is given. As we can see in this diagram, this bar is having different diameters and different length, so it is called as a stepped bar. Here we have to take capital E, that is Young's modulus, as 210 GPa. Now whatever is given here, I'll write that in the form of data. 20 mm diameter, I'll write it as D1. Here the length is 0.5 meter, so I'll convert it into mm. So this will be 500 mm. Next, D2 is 25 mm. Length becomes 700 mm because it is 0.7 meter. Next, diameter is 30 mm. Length is 900 mm. Now, apart from this, as we can see, this system is subjected to different loads, and here they are telling to calculate the magnitude of P for equilibrium and total elongation. So magnitude of P is the unknown and total elongation, that is delta L. These are the two unknown quantities which we have to calculate. So let us try to get the solution for this problem. Solution. First, I'll go on to find the value of unknown load P. For this, as we see in this problem, all the forces are horizontal. So for the equilibrium condition of this stepped bar, I'll say that sum of all horizontal forces are equal to 0. Since for equilibrium of stepped bar, summation of Fx is equal to 0, where all rightward forces, I'll take them as positive, all leftward forces negative. So therefore, if we look into the diagram, here we have minus 10 plus 5, minus 10 because it is acting towards left, plus 5 since it is acting towards right, minus P and plus 20 is equal to 0. So from this, if I calculate, here I'll be getting the value of P as 15 kilonewton. So this will be the first answer. Next, after getting the value of unknown load, here as the stepped bar is given in 3 different sections, I'll call this first section. Here we have the second section, and here the third section. As their diameters are given, the first thing is we can calculate the area for all 3 sections. So here I'll write down, since cross-sectional areas of all sections, it will be given by the first section area, I'll denote it as A1. So it is pi by 4 into the diameter is 20 square. This comes out to be 314.16 mm square, first area. Similarly, the second cross sectional area, diameter is 25 mm, and my answer is 490.87 mm square. At last, the third area, diameter is 30 mm, so this area comes out to be 706.86 mm square. Now, after getting the individual areas, as we have to find out the total elongation. So in this step bar there are different loads, different values of load. So we need to know how much load is acting on the first section, on the second section and third section. And for this purpose we have to take different sections separately and find the value of load. Always in such kind of problems, when you want to find out the load of individual section, try to find the load first on the extreme most section. That is, first we will find out the load on section 1 and section 3. At last we will go on to section 2. So starting with section 1, I'll separate it. This is section 1, having diameter 20 mm and the length of this section is 500 mm, 0.5 it is meter, so it is 500 mm. Now here it is given that at section 1 we are having 10 kilonewton load towards left. So here I'll mark 10 kilonewton load towards left. To balance this 10 kilonewton we have to add another load which should be towards right, having the same value, so that this section comes into equilibrium. So here this is the first section. And now after we have calculated this load for the first section, next similarly what we can do here is that after getting the value of load here, I can calculate the deflection of this individual section. So here I'll say that therefore deflection in section 1 is given by delta L1 is equal to PL upon AE for the first section. So therefore deflection in the first section is, P is tensile, so we have to take it as positive, 10 into 10 raised to 3. Length of the section is 500. Cross sectional area we have calculated for the first section, and that was 314.16. Next, capital E, the value was given in the problem as 210 GPa. So it is 210 into 10 raised to 3, because 1 GPa is, I'll write it down here, 1 gigapascal is equal to 10 raised to 3 Newton per mm square. So in this problem they have given 210 gigapascal. So it is 210 into 10 raised to 3 Newton per mm square. Now from this I will get deflection in the first section. My answer is, it is 0.076 mm. And since this answer is positive, it means there is elongation in the first section. Next, similarly here, after separating the first section, now I'll separate this third section, because as I have told before, we have to start with the first and the last section, that is extreme sections, and then the middle portion. So here I'll separate this portion which has a diameter of 30 mm and length is of 900 mm. Length is 900 mm. Now, as we can see in this problem, in the third section we are having two loads, that is, first is 20 kilonewton and the other is load P. But this load P will give us the value at the junction. So it is better to find the load at only individual end. So here I'll start with this 20 kilonewton which is acting towards right. Now here, as I can see, 20 kilonewton is applied towards right. So for the equilibrium condition of this beam, here I have to add another 20 kilonewton which is towards left. So because of the action of these two forces, there is tensile load acting on this beam or the section of the stepped bar, and it is subjected to tension. So here I'll calculate the deflection since deflection in section 3 is given by delta L3 is equal to PL upon AE for the third section, so therefore delta L3 will be equal to, here P is 20 kilonewton, so 20 into 10 raised to 3, length is 900 mm, area for the third section, the value was 706.86, Young's modulus, it is 210 into 10 raised to 3. So from this, the deflection in the third portion, it comes out to be 0.121 mm. Again, as this value is positive, it means there is elongation. Next, after finding the elongation in the first and the third section, now we will separate the middle portion. That middle portion is having a diameter of 25 mm. And its length is 700 mm. This is the second section for us. Now, as we can see, on this second section, there are two load values. One is 5 kilonewton, other is P. So what is the value which we have to take? Now, if we look into this, at section 1, when we have separated it, there was 10 kilonewton load towards left, 10 kilonewton towards right. Now this 5 kilonewton towards right is the load at the junction. So now how I'll explain this is that 10 kilonewton load is there at this junction. It is, we can say, because of section 1. Now because of section 2, there is also another value of load. If you add 10 in that value of the load which is there on the section 2, that should give you an answer of 5 kilonewton towards right. So how we can complete this is that here we already have 10 kilonewton. So if we want the answer is 5, then we need to subtract 5 from this. So if at this junction I have another load which is of 5 kilonewton towards left, then by adding them my answer will become 5 kilonewton which would be towards right. So here we can complete this by adding a load of 5 kilonewton towards left at second section, because here this is going towards left, so minus 5. Next, at the same point we are having plus 10, so minus 5 plus 10, that gives us plus 5 kilonewton. And so here we are saying that this condition has been met or it is satisfied. And to balance this, we have another 5 kilonewton load onto the other side. So now if we can see the value of load P, it was 15 kilonewton, 15. So we can calculate this at section 3. Here when I have separated, 20 kilonewton load is already there. Now there is another 5 kilonewton load here. So 20 is towards left, so minus 20, and this is 5 which is plus, so minus 20 plus 5, that gives me 15 kilonewton, and that 15 kilonewton load would be acting here. So the diagram is satisfied. So here I can calculate the deflection for the second portion, that since deflection in section 3 or section 2, I can say section 3 is over, is given by delta L2 is equal to PL upon AE for the second section. Now here I will be putting the values. Therefore delta L2 is equal to P, as we see Second section, it is subjected to tensile load, so P has to be taken positive, so positive 5 kilonewton. If I write into Newton, it is 5 into 10 raised to 3. Next, its length is 700 mm divided by area of second section, that was 490.87 into Young's modulus is 210 into 10 raised to 3. So here I have this deflection as 0.034 mm, and again, since my answer is positive, it means there is elongation. So after getting these three deflections, we can get the total deflection by adding them. So here I can say that therefore total deflection is given by delta L is equal to delta L1 plus delta L2 plus delta L3. So therefore total deflection is equal to delta L1, the value we have found out, it was 0.076. Delta L2 just now we have calculated 0.034. Delta L3 it was 0.121 mm. If I add up these values, my answer comes out to be 0.231 mm. And since this answer is positive, second answer for us, so here this means there is elongation or increase in length of the step bar. So here in this video we have seen how to calculate the value of unknown load P, which was the first question, and the total deflection, or we can say elongation, of the step bar. So both the questions have been solved, and with this we complete the problem.